Welcome to this video on warping torsion. This is one of several videos in a short course on structural members posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. As we saw in the video on St. Venant torsion, torsion means that a beam or frame member is twisted about its longitudinal axis. The rotation is denoted by the Greek symbol phi, and the torque, which is the resultant of shear stress in the cross-section, is denoted by the letter T. The double arrow means rotation about the axis of the arrow. The St. Venant theory for torsion, addressed in another video posted at terje's Toolbox, assumes that zero axial stress develops when the beam is twisted. St. Venant torsion includes shear stress only. Warping torsion, which is addressed in this video, accounts for the fact that axial stress sometimes appear when the beam is twisted. The wide flange beam shown in this slide illustrates the fact. First, notice on the right-hand side, marked with red color, that there is a different amount of axial displacement at different locations in the cross-section. This is called warping. A wide flange cross-section is an example of a cross-section that warps. Next, we turn our attention to the left-hand side, where the beam is completely fixed. Observe that the upper flange, marked with solid blue lines, is bending like a cantilevered beam. Similarly, the lower flange, marked with dashed lines, is bending in the other direction, also acting as a cantilevered beam. From Euler-Bernoulli beam theory and simple structural analysis for a cantilevered beam, we know that a bending moment and associated axial stress develop at the fixed end of the beam. In other words, the beam wants to displace in the axial direction at the left end, just like it is allowed to do at the other end. But we restrain that axial displacement on the left-hand side. It is the fact that we restrain the warping at the left-hand side that makes axial stress develop there. This is an example of axial stress developing from torsion of the beam. To summarize, two conditions must be met before torque is carried by axial stress. First, the cross-section must be of a type that warps. The beam with a circular cross-section shown at the bottom of this slide does not satisfy that condition. That is because the cross-section does not warp when the beam is twisted. All points along the circumference of the cross-section have the same axial displacement. We will soon review which cross-sections warp and which cross-sections do not. However, let us mention the second condition that must be met before torque is carried by axial stress, namely that we must restrain the warping somewhere along the beam. The cantilevered beam shown on this slide, which is completely fixed on the left-hand side, preventing axial displacement, is one example of restrained warping. The next slide shows another example, where it is not the supports that restrain the warping. This is a simply supported beam resting on fork-type supports, meaning that warping is not restrained at either end. However, when the beam is subjected to a torque applied at mid-span, we see how the flanges again act like beams that are being bent, meaning that they develop axial stress. The next slide shows cross-section types that either warp or do not. Cross-sections that do not warp include thin-walled cross-sections with straight parts that intersect at a single point. The X-shape and L-shape shown here are therefore examples of cross-sections that do not warp. Furthermore, cross-sections with sides of equal length that can be circumscribed by a circle, whether they are thin-walled or not, do not warp. That means the square cross-sections shown here do not warp. For these cross-sections, all torque is carried by shear stresses, that is, St. Venant torsion, regardless of the boundary conditions. On the other side of the slide, you see cross-sections consisting of straight lines that intersect at more than one location. These cross-sections will warp when the beam is subjected to torsion. These rectangular cross-sections will also warp. To understand warping torsion, it is instructive to consider a beam with a wide flange cross-section, such as the beam shown on the next slide. When torsion is applied to the beam, then the flanges of this cross-section experience bending in the flange planes. In other words, torsion induces bending about the strong axis of the flanges. The shear force in each flange is denoted by V, as shown here. Because the moment arm for those two forces is the cross-section height, h, the torque carried by warping torsion is H times V. Next, we borrow equations from Euler-Bernoulli beam theory, applied to each flange as a separate beam in bending. Because the shear force is the derivative of the bending moment, the torque is H times the derivative of the bending moment in the flanges. Next, we introduce the equation from Euler-Bernoulli beam theory that contains section integration, material law, and kinematic compatibility, shown here. As a result, the torque from warping torsion now contains the third-order derivative of the displacement of each flange. That displacement, denoted by W, is directly related to the rotation of the cross-section, denoted phi. Because the distance from the center of rotation to each flange is h over 2, we find this expression for the displacement of each flange. Notice the minus sign, because the local z-axis for the bending of each flange is the green arrow shown on this slide, which is in the opposite direction compared to where the flange is displacing when the cross-section rotates. The expression for the torque now contains the third-order derivative of the rotation, phi, as shown here. This is the final differential equation for warping torsion, except we are missing equilibrium between the torque and externally applied distributed load on the beam. That equilibrium equation is derived in the video on St. Venant torsion, and we will include it on the next slide. For now, we rewrite this differential equation by introducing a cross-section constant for warping torsion, called Cw. For the cross-section addressed on this slide, Cw is the moment of inertia for bending about the strong axis for each flange times the height of the cross-section squared, divided by 2. The result is the general notation for the differential equation for warping torsion shown at the bottom of this slide. This is an important result to keep in mind from this slide. In fact, we utilize it already at the top of the next slide. The torque from the St. Venant theory presented in another video posted at terje.civil.ubc.ca Toolbox is added to the torque from warping derived on the previous slide. Next, we introduce equilibrium between the torque and the externally applied distributed torque on the beam, also derived in the video on St. Venant torsion. The result is the complete differential equation for torsion, including both St. Venant torsion and warping torsion. This is a fourth-order differential equation with constant coefficients. As a result, we set up the characteristic equation for this differential equation as shown here. The four roots of that equation are two zeros and plus minus the square root of Gj over ECW. Accordingly, the homogeneous solution to the complete differential equation for torsion is as shown here. An example of a specific solution is shown at the bottom of the slide for a cantilevered beam that is fully fixed at x equals 0 and subjected to a torque, T0 at x equals L. That solution is plotted on the next slide by first substituting it into the expressions for torque from the St. Venant theory and the warping torsion theory. The interesting observation is made that the total torque applied at the end is primarily carried by warping torsion, namely axial stress, at the left-hand side where the warping is restrained. Conversely, as we get close to the end where the torque is applied, which is not warping restrained, most of the torque is carried by St. Venant torsion. In a sense, we can say that warping torsion is a boundary effect that diminishes as we move away from the location where warping is restrained. The next slide introduces a concept that is unique to warping torsion. It is called the bi moment, and it is introduced as an auxiliary quantity that makes the equations in the warping torsion theory mimic the form of many of the equations in Euler-Bernoulli theory for beam bending. For a wide flange cross-section, the bi moment is defined as the moment in each flange multiplied by the distance between the flanges. You will understand from that definition that the bi moment is not a physical quantity that is easily visualized. Instead, the figure shown at the top of this slide, with the two double arrows for the flange moments and the cross-section height, W, is as close as we get to visualizing the bi moment. Once the bi moment is defined in this manner, we can introduce the equation from Euler-Bernoulli beam theory that contains section integration, material law, and kinematic compatibility. That gives the expression for the bi moment shown here. Next, we introduce the expression for the displacement, W, in terms of the cross-section rotation, phi. That gives the expression for the bi moment shown here. Finally, we introduce the definition of the cross-section constant Cw that we introduced earlier. The final result is shown at the bottom of this slide. This is another general equation in warping torsion theory that we take a note of. The bi moment is the warping stiffness times the second-order derivative of the torsional rotation. At this point in this video, we have only seen warping torsion for wide flange cross-sections. Next, we will derive the general theory for warping torsion of other cross-section types. As usual for the boundary value problems that structural members represent, we will address equilibrium, section integration, material law, and kinematic compatibility. The derivations will actually establish a unified theory for bending and torsion of thin-walled cross-sections. The theory is named after a person named Vlasov. Because warping torsion and beam bending are both formulated in terms of axial stresses, it is possible to combine the two theories. The omission of shear deformation in Euler-Bernoulli beam theory is carried over to the warping theory that is presented next. It is possible to include shear deformation, as is done in Timoshenko beam theory. That is done in the document on warping torsion posted at terje.civil.ubc.ca, Toolbox, but it is not included in this video. The next slide shows equilibrium equations that match exactly those derived in the videos on truss members, Euler-Bernoulli beams, and St. Venant torsion. The blue and red arrows show the direction of the bending moment and shear force in the two-axis directions of the cross-section. My is the bending moment about the y-axis. Mz is the bending moment about the z-axis. The shear forces act in the directions dictated by equilibrium of the infinitesimal portion of the beam. In summary, this slide shows the 6 equilibrium equations that belong to the unified theory of bending, torsion, and axial deformation. The next slide shows the section integration equations for this unified theory. The axial force is simply the integral of axial stress over the cross-section. The two bending moments are obtained by integrating axial stress multiplied by the distance from the centroid of the cross-section to the fiber where the stress is acting. The red and blue arrows show the direction of these moments in the cross-section. Remember, a double arrow means bending about the axis of that arrow, with the direction of rotation being the same as the rotation of a screwdriver when you fasten a screw. The 3 first equations on this slide are essentially taken from the videos on truss members and Euler-Bernoulli beam theory. It is the equation for the bi moment that is new here. Notice that the equal sign is written in a way that means this is a definition. The bi moment is here defined as the axial stress times a quantity denoted by the Greek symbol omega. It is the first time we see omega in this video, but this is a very important quantity in warping torsion. It is a central quantity in the theory presented on the next slides. For now, notice how the omega enters in a way similar to the appearance of y and z in the equations above. This is a good way to understand the bi moment, b, and the omega quantity. Namely, the definition of those quantities make the governing equations for warping torsion match the form of the equations from Euler-Bernoulli beam theory. The material law given at the bottom of this slide is simply Hooke's law. It specifies a linear relationship between axial stress and axial strain, which is the stress and strain that we consider in this unified boundary value problem for bending and torsion. The next slide starts the kinematic compatibility derivations. This is a large portion of the theory presented in this video. The ultimate objective is to establish a relationship between the axial strain and the displacements u, v, and w, as well as the torsional rotation, phi. In terms of notation, let the coordinate s follow the center line of the contour of the cross-section and let a lowercase h denote the distance from the center of rotation of the cross-section, namely the shear center, denoted by ysc and zsc, to the tangent of the coordinate line s, as shown in this figure. Notice that the y and z axes originate at the centroid of the cross-section and that the shear center coordinates ysc and zsc are unknown, for now. As a fundamental kinematics postulation, it is assumed that the cross-section retains its shape. This implies that the displacement in the s direction, labeled v tilde, is this expression. Notice that v and w are the displacements of the cross-section and that alpha is the angle between the s-axis and the y-axis. The contributions to this expression are illustrated in bottom figure on the left-hand side. Notice that one contribution to the displacement v tilde is the rotation of the cross-section, phi, times the distance, h, from the center of rotation to the tangent line of the s-axis at a point. This contribution is central in warping torsion. The figure also shows how the sine and cosine functions are expressed in terms of the differentials ds, dy, and dz. The result is shown in the bottom equation, which expresses that the cross-section retains its shape during deformation. On the next slide, we first highlight that the boundary value problem is formulated in terms of axial stress and strain, meaning that the equation epsilon equals du over dx is the fundamental kinematics equation for the boundary value problem at hand. Next, an expression for du is sought, namely the infinitesimal axial displacement, that is, warping, between two infinitesimally close points in the cross-section. The red box and the figures on the left-hand side shows that shear strain, gamma, is related to the infinitesimal axial displacement du because that shear strain has two contributions. The one illustrated in the top figure is du over dx. The one illustrated in the figure below is dv tilde over dx, where v tilde is the displacement along the s direction. In the red box, we also solve for du and substitute the expression for v tilde from the previous slide. The expression is organized so that the contribution from the rotation of the cross-section and the contribution from the shear strain gamma xs appear inside a parenthesis. This parenthesis is the contribution to axial deformation from torsion. In other words, this is the warping torsion term. An important point regarding this term is that the shear strain gamma xs is often zero. From cross-section analysis for St. Venant torsion of thin-walled cross-sections, we know that the shear stress and therefore the shear strain is zero in the midline of the contour of the cross-section, where the s-axis is running. However, for closed cross-sections with one or more cells, gamma xs is non-zero, so that case must be addressed as well. For now, we will ignore gamma xs in order to focus on the other torsion-related contribution to the axial displacement. That contribution is shown in the last term in the equation below the red box, where the infinitesimal axial displacement du is integrated in order to obtain an expression for u itself. Notice that the integral around the cross-section of the distance h appears. It turns out that this is exactly the omega quantity that we compared with a cross-section coordinate a few slides ago. The expression for omega is shown in the green box on this slide. We can now make the following statements. First, we determine omega by summing h times ds as we walk along the s-axis around the cross-section. Second, the result can be drawn in a diagram that follows the contours of the cross-section. We call this the omega diagram, which is the central objective in cross-section analysis for warping torsion. Third, the expression for omega must be amended for closed cross-sections because gamma xs is then non-zero. That will be done shortly. The last equation on this slide shows the kinematic compatibility equation that appears when we substitute the expression for the axial displacement, u, into the strain expression from the top of this slide. On the next slide, we address a closed cross-section with one cell. Such a cross-section is illustrated on the right-hand side. We know from St. Venant torsion of closed cross-sections that the shear strain, gamma xs, is non-zero along the midline of the cross-section contour. It is now desirable to express gamma xs in terms of the cross-section rotation, phi, so that the rotation can be pulled outside the parenthesis that appeared in a red box on the previous slide. This is achieved by utilizing equations from the theory of St. Venant torsion. First, the material law is spelled out. Next, the expression for the stress in closed cross-sections is taken from the St. Venant torsion theory and shown here. K is the amplitude of the stress function and T is the thickness of the wall. For single-cell cross-sections without free flanges, that amplitude is determined from the next equation, which is the expression for the torque in a closed cross-section with one cell, also taken from St. Venant torsion theory. For a given torque, T, we get the constant K because we know the quantity Am, which is the area of the cell. As a result, the shear strain for one-celled cross-sections without free flanges is as shown here. Notice that the St. Venant torsion equation that equates the torque, T, with Gj times the derivative of the rotation, phi, is utilized here. That gives the following revised formula for omega for closed cross-sections. The fraction that is new for closed cross-sections is often denoted by h bar and is referred to as the shear radius of the cross-section. All quantities in that expression is known from St. Venant torsion. A few additional considerations are necessary for cross-sections with more than one cell and potentially free flanges. Although this video does not address that problem, the note on warping torsion posted at terje.civil.ubc.ca Toolbox and the examples of cross-section analysis posted on the same website show derivations and practical applications for multi-cell cross-sections. In this video, we have now established all the ingredients of the boundary value problem for unified bending and torsion of thin-walled cross-sections, with emphasis on the new quantity that we call omega. It is time to combine all the ingredients in order to formulate the differential equation of the boundary value problem. Actually, 4 differential equations will appear. 1 for axial deformation, 2 for bending about the 2 axes of the cross-section, and 1 for warping torsion. This slide starts by combining material law and kinematic compatibility, shown in the green box. Then that expression for axial stress is employed in the section integration for axial force, bending moments, and the bi-moment. The resulting 4 equations are here shown in vector matrix form in the red box. This looks messy, because it appears that the axial force is coupled with both curvatures and even the torsional rotation. Many other couplings also appear. However, if we make smart choices, then all the equations become decoupled, appearing as shown in the blue box at the bottom of this slide. We will look at the conditions for decoupling on the next slide. For now, notice that we have defined 4 cross-section constants in order to simplify the expressions. They include the cross-section area and the 2 moments of inertia known from truss members and Euler-Bernoulli beam theory. The most important constant in this video is the last one, labeled Cw. This is the cross-section constant for warping torsion. Notice that it is the integral over the cross-section of omega squared. Again, we see the similarity in the form of this equation with the equations from regular beam theory. The moment of inertia is the integral of y squared or z squared, and the cross-section constant for warping torsion is the integral of omega squared. On the right-hand side of this slide, we have introduced equilibrium with externally applied loads in order to arrive at the differential equation for truss members and Euler-Bernoulli beams derived in other videos at terje.civil.ubc.ca Toolbox. It is notable that we obtained those equations from the unified bending and torsion theory presented in this video. The full differential equation for torsion will be addressed shortly, but first we see on the next slide the conditions that must be met for the equations to be decoupled. In other words, we wish to review the conditions that must be met for the 6 off-diagonal elements of the matrix on the previous slide to vanish. These 6 conditions form an important part of any cross-section analysis. The first 2 conditions determine the y and z coordinate of the centroid of the cross-section. We must let the y and z axes originate at that point. The next conditions say that we must align the y and z axes with the principal axes of the cross-section. For many cross-sections, this is automatically satisfied when we let the y and z axis be in the horizontal and vertical directions. The next condition says that we must normalize the omega diagram so that its integral over the cross-section is 0. This gives rise to a normalizing constant in the cross-section analysis, which is addressed in the short course on cross-section analysis posted at terje.civil.ubc.ca Toolbox. The last 2 conditions actually determine the shear center coordinates, YSC and ZSC. The omega diagram must be drawn with reference to that point, which is the center of rotation in torsion. More details are given in the note on warping torsion and in the short course on cross-section analysis. The next slide develops the complete differential equation for torsion. At the same time, we get a preview of the calculation of shear flow and shear stress for warping torsion. This is akin to the recovery of shear flow and shear stress in Euler-Bernoulli beam theory. The theory is formulated in terms of axial stress, and we recover shear stress by equilibrium afterwards. The reason why that exercise fits with the development of the full differential equation is that we have not, in the development of the unified theory in this video, worked with the torque, T rather. We have worked with the bi-moment, B. It is necessary to bring the torque into our considerations, because the equilibrium equation for externally applied distributed torque, derived in the video on St. Venant torsion and earlier in this video, contains the derivative of the torque, T, with respect to x. The first equation on this slide expresses equilibrium of the infinitesimal part of the beam shown on the left-hand side. In the same line, the equation is divided through by ds and dx. In the end, shear flow, Qs, is defined as the shear stress times the thickness, T. This is the same definition as is used in the calculation of shear flow and shear stress in beams subjected to bending. The next equation integrates shear stress over the cross-section in order to obtain the torque, T. The second equality introduces the shear flow, Qs. The next equality employs the definition of omega introduced earlier in this video. Finally, on the same line, integration by parts is utilized to switch from d omega to dqs. The boundary term from integration by parts vanishes. Substitution of the first equation on this slide into the second equation yields the third equation. By pulling the derivative with respect to x outside the integral and recognizing the expression for the bi-moment, we see that the torque is actually the derivative of the bi-moment with respect to x. That link between the torque, T, and the bi-moment, B, is the key to unlocking the full differential equation for torsion. The second last equation on this slide simply introduces the differential equation from St. Venant torsion and the definition of the bi-moment from earlier in this video. The last equation, marked with blue, further introduces the equilibrium between the torque, T, and an externally applied distributed torque, Mx. This is the complete differential equation for torsion, which we saw also earlier in this video when we looked at torsion of a wide flange beam. The final slide serves as a reminder that details of the cross-section analysis are not covered in this video. The short course on cross-section analysis, also posted at terje.civil.ubc.ca, will explain the details of how an omega diagram is established. Once that diagram is available, we can determine the cross-section constant for warping torsion, Cw, the axial stress in the cross-section due to torsion, and also the shear stress, as we just derived. Thanks for watching this video. Please visit terje's Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.